We've talked about typical savings accounts that pay either simple or compound interest where you put money in at the beginning and just leave it there. But now I want to turn our focus and attention to another type of savings account where you actually make periodic payments, not just one payment at the beginning and leave it. For instance, if you're saving up to make a down payment on a house or a car, or maybe you want to create a college fund for a child, you'd probably be interested in putting money in periodically over an extended period of time. So that's the focus of the discussion today, and that differs from the previous type of accounts, which you just put the money in once, never added to it, and just let it sit there for an extended period of time. Here, you're actively putting money in periodically over an extended period of time. An account of this type is called an annuity. If you've got a sequence of equal payments made at equal intervals into an account, it's called an annuity. If those equal payments are made at the end of each interest compounding period, the annuity is called an ordinary annuity. The time between payments is called a payment period. For instance, if you put money in once a month, then the payment period is monthly. If you put your payments in once a quarter, it's quarterly. Semi-annual would be twice a year, and annual would be once a year, and so forth. And the time between the start of the very first payment period and the end of the last one is called the term of the annuity. In other words, how long is the annuity going to last? Now, the future value of the annuity is the total amount of money in the account, including the interest, the amount you put in, plus any interest that money earned at the end of the term of the annuity. Now, we've used future value in other contexts, and future value just means what the money will be worth in the future. So you can have future value of a simple interest account, you can have the future value of a compound interest account, and you can have the future value of an annuity. And I said that we define something called an ordinary annuity where the equal payments are made at the end of each interest compounding period. In reality, that's the only type of annuities that we will be talking about, even though other types exist. So when I say annuity, even if I don't add the word ordinary, we're only discussing ordinary annuities. So if I fail to say ordinary, you can still just assume that that's implied, because we're only discussing ordinary annuities. A sinking fund is another name for an ordinary annuity. So if you see a problem that refers to a sinking fund, that's the same thing as an ordinary annuity. Now, the formula we'll be using, we're always using capital A for the future value of whatever type of account we're dealing with. So this is an ordinary annuity. So in this context, capital A is the future value, or sometimes I call it the accumulated value of the account. And the formula is given by A is equal to capital R times this fractional quantity, whose numerator is 1 plus I, that quantity raised to the n power, then minus 1, and that divided by I. And a little I is the same thing as it was before. So when I introduce a letter to represent something, I'll make sure that it means the same thing. So little I is little r over little m. In other words, the annual interest rate divided by the number of compounding periods per year, and little n is m times t, just as it was before. The only new variable in this formula is this capital R. We've seen capital A, we've seen little I, we've seen little r, we've seen little m, we've seen t. So the only new one is capital R. And capital R stands for the amount of the periodic payment into the annuity. Remember, when we just did regular compound interest, we just put the money in once and left it. We call that capital P for principal. This time, we don't just put money in once and leave it. So capital R stands for the amount we put in every period, whether it's every month or every quarter or however the period runs. So that's the only new letter. So you have a new formula, but all the variables are things you've seen before except for the capital R. And of course, as I said, the capital A is the future value, just like it was in other formulas. So if you put all this together, there's your basic formula. Again, capital A is what it always was, the accumulator of future value of the annuity. capital R is the periodic payment into the account. That's the new thing. And little I is the interest rate per period, which you get by taking the annual interest rate R divided by the number of compounding periods M. And N is M times T, just as it was before. So as I said, there's a new formula, but there's only one new variable, and that's capital R. Best way to see how this works is just to jump right into it with an example. Suppose I've got a payment of $50 to be made at the end of each month, going into an account paying 6% annual interest, and it's compounded monthly. The question is, how much will be in that account after 3 years? Well, first of all, it's an annuity because you're making periodic payments. And that's the thing that you have to remember. You're doing it at the end of each month. So you're using your formula for ordinary annuity, which begins capital A equals capital R times the fraction. So first thing, realize that it's an annuity, pick the right formula. Now you've got to identify what everything is. Capital R is the periodic payment made into that account. Well, the problem says it's $50 a month, so the R is 50. Capital R is 50. Look through, it's a 6% annual interest rate, that's little r. We write it as a decimal, which would be 0.06. Plug that in for R. It's compounded monthly, which means it's 12 times a year, so little m is 12. Plug that in for m. And finally, you need to know what t is. It's 3 years, so t is 3. Plug that in. And that tells you that if you take 0.06 divided by 12, you'll get 0.005. And if you take 12 times 3, you get 36. So you'll end up with those values for little I and n. And once you have those values, you simply plug them in to the formula. So if I take little I and replace it with 0.005 and little n gets replaced with 36, then my formula looks like this. And at this point it becomes a calculator problem. So you want to take 1 and add 0.005, and that comes out to be 1.005, of course. And 36 power, so you go use the power button on your calculator. Remember, that's the button on your calculator to raise power, as we've talked about before. So you do 1.005, power button, 36 equal to. And if you do that, you will get 1.196680525. Now, we're going to do some examples later where I'll show the actual calculator steps, but now I'm trying to do it conceptually. But what I will say is, don't round that number off. Leave it in your calculator with all those decimal places, or if you must clear it out, write down all those decimal places. If you round too early in the process, you will not be accurate to the nearest cent. So be careful. So plug that in. Now looking at the numerator of that fraction, we need to subtract 1. That gives you 0.196680525. Plug that in. Now we want to divide that decimal by 0.005. Do that on the calculator and you end up with 39.336105. Now multiply that by 50 and you get $1,966.81. So if you put a payment of $50 a month into an account at 6% annual interest compounded monthly, at the end of 3 years, you will have just under $2,000 in that account. Now you can also think about whether your answer makes sense. So if you get a crazy answer, you know you've made some mistake. If you put in $50 a month for 3 years, well, $50 a month for 1 year is 12 times 5 is 60. So it'd be $600 a year for 3 years. That's $1,800. Well, if you didn't earn any interest at all, you'd have $1,800. So $1,966.81 seems reasonable. That means you made $166.81 of interest in 3 years. That seems reasonable. And had you gotten an answer like 19,000 or something, that doesn't make any sense. So when you do these calculations and look at the final answer, take a brief moment to just look back and say, does that answer even make any sense? Because if it doesn't, you have an opportunity to go back and find your mistake. So that's a typical ordinary annuity problem. Let's do another. Suppose you want to start a sinking fund that will be worth $1,800 in 2 years, and you make quarterly payments this time, not monthly payments, but quarterly payments into the account, paying 6% interest compounded quarterly. And the question is, how much do you need to put into the account each quarter? Now this is the flip side of the previous problem. The previous problem, you knew the periodic payment and you were looking for how much was in the account at the end. This is a sinking fund, which I told you earlier is just another name for an ordinary annuity. So it's the same formula, but what you have to remember this time is that they're asking you for capital R. In the previous problem, they gave you capital R and you were looking for capital A. Now they've given you capital A and you're looking for capital R. So the main thing in this problem is to realize that you're solving for capital R, not capital A. So let's do that. Well, otherwise, the process starts off the same. You identify the numbers in the problem. You want it to be worth $1,800 in 2 years. That's the future value or the accumulated value in the account, so that's capital A. So plug it in. You got the 6% interest rate, change it to a decimal, plug in 0.06. Scanning through, it says the interest is compounded quarterly. That means M is equal to 4. You're doing it 4 times per year. Quarterly is 4 per year. Plug that in. And you're doing it for 2 years, so little t is 2. Plug that in. When you do the arithmetic, you will do 0.06 divided by 4, and 4 times 2. So little I is 0.015 and little n is 8. Plug those values into the main formula. If you put 0.015 in for little I, and then put 8 in for n, you get it to the point where it's basically, at this point, just calculator work. So the first thing you want to do is add 1 and 0.015. That comes out to be 1.015. Now you want to use the power button on your calculator to raise it to the 8th power. Again, I'll do some problems later where I actually show the calculator steps. Now I'm trying to do it more conceptually. But you can follow along yourself with your calculator, raise it to the 8th power, and what you'll get is 1.126492587. And as I said before, do not round that off. If you start rounding it off during the calculations, your final answer may not be accurate to the nearest cent. Just leave it in your calculator display. If you must take it out, write down all the digits that are displayed. Next thing we'll do is subtract 1. That just becomes 0.126492587. Then divide that by 0.015, and you'll get 8.432839133. Now you're solving for R, remember, so you need to divide both sides by that 8.432, etc. And you'll get capital R. So I need to take 1,800 divided by 8.432839133. If you do that, you get $213.45. So if you want to end up with $1,800 in 2 years with that 6% interest rate compounded quarterly, you will have to put in $213.45 per month. And again, I'll do some of the problems in other places where I'll show calculator steps and you can sort of see the calculator keystrokes. But right now, I just want to make sure you understand this conceptually. It's also probably worthwhile, if you haven't, is to watch the video on calculator tips, because it shows you some ways that you can do these calculations about as efficiently as possible. So I would suggest that as well.